Hey kids, in this lesson we're going to look at the relationship between functions, its first derivative and second derivative, and there's a lot going on here, and brilliant men have researched all this out and worked it all out, and it's totally fascinating how everything works. And what we're going to do is show a connection between all of these derivatives in the graph of the function, the original function. So what we're going to do is we're going to first start with what's called a first derivative test. And that's when you take a derivative of a function, set that derivative equal to 0, and determine where that function is equal to 0 or where it's undefined, where the derivative is equal to 0 or undefined. And once you find those specific values of x where the derivative is either 0 or undefined, then we've got what are called critical points. And a critical point is used to locate the specific places that the graph has all the different things that are going to happen to it, like a max, a min, maybe it doesn't have any extrema, and maybe we're looking specifically at a right or left endpoint. And so here's what we're going to do. You have a local maximum if the derivative, you're trucking along and the derivative goes from being greater than 0 to being less than 0. Okay? Why? Because think about this. We learned in the previous section, if the derivative is greater than 0, your original function is increasing. When the derivative is less than 0, your original function is decreasing. So what happens at this point right here? We have a max. Okay? What about a local minimum? Hey, guess what? You're going to go start off with derivative being less than 0, and then you're going to switch, and your derivative is going to become greater than 0. So just like what we just looked at, except in reverse. We're going to first be going down, then we're going to be going up. Okay. Hey, what happens if you have no extrema? Maybe your derivative does something like it goes from greater than 0 at a specific point, and then it goes, oh, whoops, greater than 0. Or you could be trucking along and your derivative might be less than 0, and then it goes to, oh, less than 0. So if something like this happens, then you don't have any extreme at all. On your left endpoint, we're looking at whether it is going to be less than 0 or greater than 0. So if the function is less than 0, well, we might have to look at some examples here. So what I'll do is I'll just say use your visual cues on left and right endpoint. Okay, use your visual cues when you graph this, and we'll check this as well. But keep in mind that if we're increasing, we're going to be greater than 0. So if we start at a specific point and start to increase, then that would be a minimum. And if we start at a specific point and then decrease, that would be a maximum. So use your visual cues on the left and right endpoints. But we would be able to tell, for example, if we come back up to what I've already drawn, if I start at my left endpoint and go up and increase from that endpoint, I have a minimum. And if I start at my endpoint and go down, I'm going to have a maximum. Okay. So we're going to find the extreme values of the following functions. We want to find the extreme values. So what are we going to do? We're going to look for derivative. F prime of x is equal to 3x squared minus 12, and we're going to set that equal to 0. And when we solve this out, we're going to get that 3x squared is equal to 12, so x squared is equal to 4, so x is equal to plus or minus 2. That's my critical points. Those are my critical points when x is plus 2 or when x is minus 2. That's going to tell me what's going on. So how can I sort this out? Well, let's create a little sign chart here. And we're going to look just at the derivative, and sign charts are really fun. We're going to look at, let's see here, will that factor at all? I don't know if that'll factor. We'll look at -2 and 2, and we want to know, what's going on with the different signs here. So when I've got 3x squared minus 12, if I put a number, and I just need the sign on this, if I put a number in, like, say, -5, just something way over here further to the left of -2. If I put a -5 in there, I'm going to get a positive value out. Okay, positive value. That means that my derivative is increasing at that point. And then I'm going to put in something like a number from in between -2 and 2, something like 0. When I put a 0 in here for x, when I put a 0 in here for x, I get 3 times 0 minus 12. That's going to be negative. And I don't care exactly what the number is. I just want to know what's the sign, the S-I-G-N. What if I pick a number like 7? What if I put 7 in, a number from this side of the number line? Put 7 right here in for x. And when we do that, we're going to get a value that's going to be positive because we're looking at 7 squared, 3 times 7 squared. So here's what's happening. My graph increases, decreases, increases again. So what can I know about this? Well, I know that that I'm going to have a max when x equals -2. And I know that I'm going to have a min when x equals +2. That's how that's going to roll. So I can use that derivative and that first derivative test to find these critical points. Okay, so take a pause for a second, or maybe, hey, I tell you what, why don't you try x squared minus 3 times e to the x. Pause the video, try it, and when you unpause the video, I will be working it out for you. Okay, so I'm going to go ahead and work this g to the x guy out. So I've got room right over here, okay? And so the first thing I need to do is find derivative. And in order to find derivative of this guy, we got to remember that we've got the product rule going on here. So if g prime of x, then what I've got is the first, x squared minus 3, times the derivative of the second, which is e to the x, plus the derivative of the first, which is going to be 2x times the second, which is e to the x. I'm going to set that equal to 0. And to solve this out, I'm going to, let's see, will anything work here? I don't know. I've got x squared e to the x minus 3 plus, minus 3 e to the x plus 2x e to the x. And all of that equals 0. And I've got e to the x in everything here. So what I'm going to do is I'm going to factor out e to the x, and that's going to get me x squared minus, let's see, let's organize it, plus 2x minus 3. I think that's what it's going to end up being. Let me just double check e. Okay, that's it. And what I can do now is I can set each piece equal to 0. So I can set e to the x equal to 0, and then I can set x squared plus 2x minus 3 equal 0. And what that's going to do is it's going to give me the things to work with on this. Now, e to the x will never equal 0, ever, because e to the x is always above the x-axis, so it never actually crosses the x-axis. We don't even have a place where it's where this guy is undefined, so we can't really use that spot. But what I can do, though, is I can factor out my bottom, and when I do that, I end up with x plus 3, x minus 1. Okay, so when I factor out the bottom, I get x plus 3, x minus 1. And notice that's going to give me a 2x in the middle. So I've got a 0 at -3 and a 0 at 1. And what I want to do now is I want to check with these values the sign. I don't care what the value is. I just want to know what the sign is. And we'll check with e to the x because we're looking at the derivative. We'll check e to the x. We'll check x plus 3. And we'll check x minus 1. We're going to check each one of these different pieces. So when I put a number like -3 in, okay, I can't use that, it's going to give me 0. So I'm going to use -4. When I put a -4 in for x, I'm going to get a positive value with e to the x. When I put -4 into x plus 3, I get a negative value because it's going to be -1. And when I put -4 into x minus 1, I get a negative value. And so if I do a positive times a negative times a negative, okay, then this whole side right here is going to be positive. So if you multiply all these guys together down here, this will give you a ginormous plus. Okay, the whole derivative in this part is going to be positive. Okay, well, let's look at the next one. So if I take a number from inside here, say 0, okay, then when I put 0 in for x, I'm going to get a plus because, again, e to the x never crosses the x-axis. When I put 0 in for x plus 3, that gets me a positive 3, so that's also a plus. And then when I put 0 in for x on this last one, x minus 1, that gives me a negative sign. So a positive times a negative, that is a big old ginormous negative. So this middle guy then, the derivative is negative right here. Okay. Lastly, if I pick a number bigger than 1, say 5 or 2, when I put it in for e to the x, that's definitely positive now. We're growing exponentially. When I put 5 plus 3, that's positive, that's 8. And when I put 5 minus 1, that's positive, that's 4. Okay, so this whole guy is positive, and what that tells us then is this whole part is going to be positive. So when we look at this problem right here, and we're trying to find extreme values, if we were to graph that, we have a positive slope, positive, then we have a negative slope, negative, then we have positive again. So if I go from positive to negative, that's going to get me a maximum. When I go from negative to positive, that's going to get me a minimum. So we would say for this problem right here, I'm running out of room, we have a maximum when x equals -3, and we have a minimum when x equals 1. And I don't have my graphing calculator super handy right now, but we can find those y values. If you want to know a y value, you just plug in the -3 for x here and -3 for x here. It will give you a y value. Let me see if I see it. 2.99. So, and then the minimum when x is equal to 1, it would be negative 5.437. So here's your max and min values. And if I didn't list with the y coordinates earlier for this guy, you can find those out. Go ahead and practice that right now on your own. All right, concavity. That's going to be tied in with second derivative. So f of x, our function, is concave up if y prime is increasing on its interval. So y prime has to increase. F of x is concave down if y double prime is decreasing on its interval. So this needs to be double prime right here. So that's a whoopsie instead of prime. What does concave up mean? Concave up just simply means that like a mirror or something like that, we have this sort of a shape going on where we've got a curve in our graph and the top part is open. A concave down would be where the top part, is pointed down. I don't know. But concave up, this is up right here. This is down right here. So here's concave up and down. It's just the curvature of the graph, okay? So concave up happens when y prime increases. So when y prime is greater than 0. Concave down happens if y prime decreases. Okay? And you have a point of inflection when y prime is equal to 0. Okay, you've got a point of inflection when y prime is greater than 0. You could also say that you're looking for y double prime to be greater than 0 and y double prime, not pi, y double prime to be less than 0. Okay, so pretty cool. And at this point where the derivative equals 0, that's our point of inflection. So let's check it out here. Determine where the function is concave up or down, and we're going to look at x squared. Okay, and we're going to look at the interval from 3 to 10, not including 3, not including 10. So the derivative, first derivative, is 2x. Second derivative is 2. So what does this tell us? Well, let's set the first derivative equal to 0. X equals 0. Okay, no problem. Second derivative is 2. So what does that tell us? Where is it concave up or down? Well, something's going on at 0, all right, because that is the place where our derivative is equal to 0 as far as finding a maximum or minimum. But we're not allowed to use 0 because it's outside of our interval. So then we go to our second derivative now because we're trying to determine concavity up or down. Okay, that's what we're really interested in. Well, if you look down here at 2, that's our second derivative, and 2 is positive. That's greater than 0. Okay, so 2 is greater than 0. And since that's true, from 3 to 10, we are concave up. Okay? Now, think about what you know about the graph of x squared. Think about what you know. Okay? It's going to be a shape like this. Let me put the actual graph in a different color. It's going to be a shape, something like this. All right? This is totally concave up the whole way. And we're not interested in the whole graph though, because what the question said was the question said, hey, we're going to start here at 3 and we're going to go over here to 10, and we're just interested in this part. Well, that little piece of the pie, that little piece right here, from here to 10, that's what we're interested in. Well, that's a concave up shape, and we can tell that because our second derivative is greater than 0. Okay? Okay, now let's look at the second part here where y is equal to 3 plus sine x. Again, we're looking from 0 to 2 pi. So, if you think about what's going on with that graph, so our original graph is going to be, up at 3, and we're going to go up, we're going to come down, and we're going to go back. And so here's our 0 to 2 pi graph. And if you don't remember, use a graphing calculator to crank it out, but you're looking at pi being right here and 2 pi being right here. So pi over 2 and 3 pi over 2. And what we're going to do then is we're just going to try and figure out, obviously, this part right here, this is concave down. And obviously this part right here, this is concave up. Okay. So we need to find out at what point are we switching from concave down to concave up. And there is a specific point on that. So what do? We find derivative. And the derivative of 3 is 0. Derivative of sine x is cosine x. Okay. Second derivative of the cosine is negative sine x. Okay. So what we want to do is we want to find where these are equal to 0. Okay, so where's the sine of x equal to 0? And the sine of x is equal to 0, and we're looking at right here at these from 0 to 2 pi. 0 is not included, okay? But the sine of x is equal to 0 at 0 and pi and 2 pi. Okay, but remember we can't include the 2 pi and the 0 part, but we do need to use them as our guide to determine what is going on. So we're gonna start here at 0. We're gonna go to 2 pi. Whoops, let's call this guy pi and 2 pi. And we're gonna make a sign chart because where we change from concave up to concave down is our point of inflection. And there is a change in that because the sine curve doesn't sit still at all. So we're going to take negative sine x and put him over here. And then we're just going to plug some numbers in. So if I go from 0 to pi, okay, if I go from 0 to pi, my sine curve is going to be negative, okay, because it's a negative in the front. So any value from there would take on that guy. And then when I go from pi around to 2 pi, the sine curve is going to be positive. Okay, so what does that mean? That means from 0 to pi, and you can pick any point in here. For example, you can pick pi over 2, and you can pick 3 pi over 2. That'll make this a true statement. All right, and when you check these 2 points, you're going to find that you get a negative number and a positive number. And check it out, it matches our graph. Look, we're concave down here, we're concave up right there. And where does it change? It changes at pi. So we're concave down, then we're concave up, and we can determine all of that from second derivative. Okay, so finding the points of inflection, that's really similar to what we did on the previous problem. We even talked about finding that point of inflection, and that's where we're going to try and find that second derivative and where the sign changes from plus to minus on a sign chart. So if I have the derivative of this guy, that's going to be e to the negative x squared times the derivative on the top, which is this. So negative 2x e to the negative x squared. The second derivative then is now going to require some product rules. So it's the derivative of the first times the second plus the first times the derivative of the second. Well, e to the negative x squared. Well, let me just back up. We know exactly what that is. It's going to be the first times the second, the derivative of the second. Well, there's the derivative of e to the negative x squared. So negative 2x e to the negative x squared. All right, so clean this up just a little bit so we can sort through what's going on here. And this is negative 2e to the negative x squared plus 4x squared e to the negative x squared, and we want to know where that equals 0. Well, looking at it this way is really tough. It's hard to say exactly, but if you'll notice, I have an e to the x squared right here and an e to the negative x squared right here, so I can factor that out. And when I do that, I end up with negative 2 plus 4x squared. And so what I do is I set that both pieces equal to 0. So that e to the x, e negative x squared equals 0. And does that ever happen? No, it doesn't. It's always bigger than 0. And then I go with the other guy, negative 2 plus 4x squared equals 0. And I'm going to solve this guy out. I'll move up here and have a little more room. So this is going to be 4x squared equals 2, so x squared equals a half, and so x equals 1 over plus or minus 1 over the square root of 2. And so I just make my sign chart and I use the plus or minus 1 over the square roots of 2's to work this out. So I got negative 1 over radical 2 and positive 1 over radical 2. And those are the two places that I'm going to check. And I check it in that second derivative, in the two pieces of the second derivative. Here's one piece right here. Here's one piece right here. Okay? So we saw that e to the negative x squared will always be positive no matter what. Okay? But now we just need to look at what's going on then when we plug these values into negative 2 plus 4x squared. And again, I just need to know the sign. What's the sign? Is it positive or negative? So we want to pick a number less than 1 divided by radical 2. So, you know, a real safe number in this case might be negative 3. Okay? So pick negative 3. Make sure that you're picking a number that's well into that area. So I put negative 3 in here, and I'm going to get negative 3 squared, which is 9. Okay, times 4, which is 36 minus 2, so I'm going to get a positive number. And then I'm going to pick a 0, and when I put 0 into negative 2 plus 4x squared, I end up with a negative. And then pick another pick another number larger than 1 divided by square root of 2. And if you need to know what that is, punch it in on your calculator, get a decimally answer, and when you've done that, then find a larger value. But you could use something like even say 5. So, and again, just like the on the way over here on the left, you're going to end up with negative 2 plus 4 times 25, and that's a positive. So what does that mean? That means that I am concave up here, I'm concave down here. I'm concave up here. Why? Because I have a minus sign, a plus sign, and a plus sign. So I've found my points of concavity. My points of concavity, my points of inflection are right here at these two points. They are my points of inflection. So when x equals negative 1 over root 2 and when x equals positive 1 over root 2, I get that point of inflection for my graph. Now, where does that occur? I don't know. What I can do, though, is I take this negative 1 over square root of 2 and plug it into my original function. And the reason I plug it into my original function is I want the point of concavity for my function, for y equals negative x squared. And so to find that, I'm just going to go y equals e to the negative x. What is my x? Well, it's negative 1 over root 2 squared. Okay? Well, what is that? 1 over the square root of 2 squared is 1/2. All right, a negative 1/2. So my y value then for this guy is e to the negative 1/2. And it's going to be the same thing over here. So both of those guys will be points of inflection for this particular problem. So I'll write them right here. So I've got the point of inflection is going to be negative 1 over root 2 e to the negative 1/2 and 1 over root 2 e to the negative 1/2. Both of those will be points of inflection for this particular problem. Now, why don't you try x cubed minus 12x minus 5? It's a lot easier to work with. You don't get any like really totally horrible numbers. You may get a decimal or a fraction or something like that. You try it out, pause the video, you try it out, and I'll show you the answer when you start your video back up. All right, so first derivative, did you get it right? Whoa, wrong button, wrong button. Y prime is 3x squared minus 12. Second derivative is 6x. So we just need to know where 6x is equal to 0. And again, it's that's not too bad. It's at 0. So when I work out a little quick sign chart, I've got 0 here, and I've got 6x right here. And pick a number. Pick any number. Pick negative 1, pick positive 2, and you get negative, positive. So what's your point of inflection? Point of inflection occurs when x equals 0 because we're concave down, then concave up. So what y value is that? I don't know, but I can plug it back into my original function. So when I look at f of 0, I get 0 cubed minus 12 times 0 minus 5, which ends up being the point 0, negative 5 as my point of inflection. That's where my graph turns from concave down to concave up. Well, second derivative test. The really cool thing with this is you can find out where your local max and mins are based off of the second derivative. So you don't always need to use first derivative rules. In fact, if you want to take a second derivative, all we're looking for maximum is where your second derivative is less than 0. That's a little bit weird thinking, but it's true. And that gives you a local max. If you want your local min, try and find where your second derivative is greater than 0. That will be where your local min is. And so we can use that second derivative test. Now, sometimes that second derivative test is really difficult. Like there's a lot going on and we don't want to go that. We would rather solve it out from that first derivative spot. But sometimes finding that second derivative isn't too bad. And we can find where that maximum or minimum value occur.
The code word is boogers.
What? Look right at that green light and say it one more time.
The code word is boogers.
There you go. Okay, a lot going on with this one. We want to identify extrema. We want to find increasing, decreasing intervals. We want to find concavity. We want to sketch a possible graph. Oh, by the way, we're given the derivative. Okay, so what does that mean? Well, if I know that 4x cubed minus 12x squared is my derivative, I can start off by just setting that guy equal to 0. So 4x cubed minus 12x squared equals 0. This will tell me where my function increases and decreases. And to do that, I'm just going to factor out a 4x squared from everything here. and set each piece equal to 0. And I'm going to have x equals 0 and x equals 3. So when I make my sign chart, this is for increasing and decreasing behavior. Okay, I'm going to have 0 and 3. And what I'm going to do is I'm just going to look here at 4x squared, and I'm going to look at x minus 3. And I'm going to pick a number, -2, and I'm going to put it in. I'm going to pick a number 1 and put it in. I'm going to pick a number 5 and put it in. So I'm going to put -2 in for all these things. Well, that's going to be positive the whole time because a negative number squared is positive, and a positive times a positive is positive. So again, I don't need to know what the exact answers are, but I'm positive here. When I put 1 in, 4 times 1. When I put 5 in, 4 times 25. Now for the negative side, for the x minus 3 part, put -2 in and I get a negative number. Okay, -2 minus 3. When I put 1 in, I still get a negative number. And then when I put 5 in, I get a positive number. So what do I get from this? Here's what I'm going to learn. I'm going to learn that I have decreasing, my function is decreasing. Something happens at 0, it decreases again, and then it increases at 3. Now I can't draw my graph yet because I need concavity. So what are my increasing intervals? My intervals increase. I increase from 3 to infinity, and I decrease from negative infinity to 0 and from 0 to 3. That's all I know. Now I don't know how it's decreasing. It could be doing a bunch of wacky stuff. Now, second derivative. What's that going to be? Take the derivative of the first derivative. So it's going to be 12x squared minus 24x. And set that guy equal to 0. So when I do this, I can factor out a 12x. Whoops, that should be 1x. So that should be x minus 2. Set each piece equal to 0, and you get x equals 0 and x equals 2. And make one more sign chart here. And we'll use 0 and 2 as our values. And so we're going to check 12x, and we're going to check x minus 2. Let me move that over a little bit. We're going to check these two values, and again, we're going to check it on numbers in these ranges. You can pick whatever number you want. You just need to pick numbers that are inside these 3 different areas that we've created on our number line. So when I put -2 in, I get a negative on the top. When I put 1 in, I get a positive, and this is in 12x. And when I put 4 in, I get positive. And how do I know that? Because -2 times 12 is a negative number. 1 times 12 is a positive number, and 4 times 12 is a positive number. Now check x minus 2. When I put -2 in, I get a negative number. Okay, -2 minus 2 is negative. 1 minus 2 is still negative. And 4 minus 2 is now positive. So what does this mean for us? Well, it means that I'm positive here, so that means I'm concave up. I'm negative here, which means I'm concave down. And I'm positive here, which means I'm concave up. Now, let's go back up here and check this guy out. I'm negative, so I'm decreasing. I'm negative again, so I'm decreasing. And then I'm positive, so I'm increasing. So we're going to add all this together, and we're going to graph it over here on my graph. And I know that I got crazy stuff happening at 1, I got stuff happening at 3, and I've got stuff happening at 2. And I don't know exactly what this graph is going to look like, but I can put a pretty good shape on it. Maybe not an exact shape that we would want it to have, but we can get a good narrowed down feel. So I'm concave up but decreasing to 0. Okay, well, what value am I at when I put 0 into my equation up here? So 4 times 0 minus 12 times 0. Okay, so I'm concave up and decreasing to 0. And I shouldn't have done that because that's my derivative, not my original. Then I'm concave down and decreasing to 2. So notice I'm concave up. So now I'm concave down and decreasing to 2. Okay? And at 2 then, at 2 I become concave up, but now I'm increasing. So at 2 I'm going to be concave up and increasing. Let's see if I can get a smooth transition up. So here's a possible graph. Concave, something like that. Which my graph didn't quite resemble that shape, but this guy's a better shape than my original. It's hard to tell the concavity in there. So use this guy as your point of reference. I wish I could line him up. I don't know how to grab that whole shape. Let me see if I can grab that whole shape right here. Oh, no, I'm not going to do that. Okay. So anyway, there you go. That is tying all this together at one full swoop, and it's really, really cool to do and to see how all those things work. So anyway, that's why these derivatives are neat. First and second derivative tests allow you to figure out and determine exactly how your graph may or may not, a good rough idea of what your graph might look like. Just set each piece equal to 0, set each derivative equal to 0, create a sign chart, and if you're not super comfortable with sign charts, just kind of watch how I did this, like what I did. You'll understand later. You just need to work through a few of these problems, just going, okay, he did this. And once you've got it, it's super handy. You've seen them before. This hopefully is just a quick memory reminder for you.